When I was a pretentious third grader sitting in math class, nothing gave me more pleasure than telling my peers off for asking the teacher what infinity plus infinity was.
Infinity is a number. It's a concept.
Yeah, we've all heard the standard script. Infinity isn't a number, it's a concept. But that doesn't mean we can't use it. There's no denying that infinity is vast, really vast. In fact, according to Wikipedia, infinity is defined as representing something that is boundless or endless, or else something that is larger than any real or natural number. Before I took calculus, I didn't really know why we needed infinity to exist. But as it turns out, the concepts behind infinity lay the groundwork for some of the most revolutionary math ever invented. Let's zoom out a bit and do some graphing. Let's look at this function y equals 1 over x. I'll plot it here. For every x value I plug into this graph, its y-coordinate is equal to its reciprocal. Now, we can't take this graph and stretch it out all the way to infinity, but we can look at how this graph acts as we get closer and closer. Let's plug in a few numbers. Try letting x equal to 100. What's your y value? Well, it would be 1 over 100, or 0.01. That's a pretty small number. Let's try 1000, 0.001. Notice how, as your x values increase, your y values decrease, but at a decreasing rate. Note how the function also never crosses the x-axis. Now, here's the catch. We technically aren't allowed by the laws of math to plug infinity in as x, because remember,
infinity is a number. It's a concept.
But I'm going to let you take a wild guess as to what this graph approaches as numbers get bigger and bigger and basically become infinite. Did you guess 0? Because if you did, congrats. Alright, let's take a look at what we just did. We took a function and analyzed its behavior as it approaches infinity. I've always felt this is a little like cheating because we're not actually doing math to get our answer, we're more just using our intuition. But this is precisely what we need to do when thinking about infinity. Because, as you may have guessed, not all functions are going to magically hit some number at infinity. But functions like our friend 1 over x that do have a limit at infinity have a lot of real-world applications. Specifically, we use infinite limits when talking about materials reaching steady states. Let's talk biology. Most ecosystems have a carrying capacity, or a maximum number of a species that can survive sustainably within that ecosystem. If we model an ecosystem as the amount of species over time, you'll see that there's a certain limit that, as time passes, the function approaches but never hits. That line, the carrying capacity, is the function's infinite limit, the point at which it would reach if it were hypothetically to go to infinity. Infinite limits are used in other scientific practices too, from chemical reactions to radioactive decay to measuring heat transfer. The concepts behind infinity also lay the groundwork for pretty much the entirety of calculus, and as fascinating as that is, I can't explain in one 3-minute video. What I hope you'll take from this video, though, is that while pretentious third grade Phoebe was right in saying that
infinity is a number. It's a concept.
It pays to take a closer look at how concepts like infinity can be applied.